Now let's talk about question 4.19. Now what you'll see is that you have a pipe entering and then a smaller pipe pushing through on this side. So the good thing about having a control volume selection is that we can select the control volume wherever we want. So let us pick the easiest spot to use the control volume, which will be the area in which the two streams meet going in and one stream exits going out. So we'll ignore the L shape of the pipe and let's just draw the control volume. We'll ignore the L shape and just use everything after that ring comes in. So I'm going to draw a nice box like this. And just so you have an idea, here is the pipe. Here is the additional pipe entering. So you can see we've chosen to ignore all of this and simply place the control volume inside of here. You also see that it says steady incompressible flow. And that implies that you are at steady state, so the triple integral term over the control volume of rho dV is equal to 0. So in your continuity equation, this term disappears. All right, so we can begin with our continuity equation and just put down the first term because we've already been given that ddt is equal to, the change with time in the control volume is 0. So we can ignore that term and we can start here, rho v n dA is equal to 0. All right, now let us fill in our control volume what our vectors are. So we know that we have one volume that is entering, so velocity points inwards, and that is, let's call it v1. So v1 will be the small circle entering, okay? We also know that our normal must always be perpendicular to and point away from the control volume. So my normal one points in this direction, and these are vectors. Then we have velocity 2 entering, and that is from the bottom of the pipe entering. So that's v2, and we know that once again our normal must point perpendicular to and away from the control volume. So we've got v1, n1, v2, n2, and we know that something must be exiting as well. So here I'm going to put velocity 3, and the normal vector points perpendicular to and away from the control volume. So now that we've got everything, let's start filling in our equation. So we know for v1, rho, v1, n1. Now remember, to turn the normal vector into a number, you simply say cos of the angle between the normal vector and the velocity vector. So this is going to be cos, and because n1 and v1 point in opposite directions, it's cos of 180 degrees. We put in the area. Now remember, area 1 is for the small pipe, so it's just a small circle, okay? A1, and I'm just going to draw a picture here so we can both keep track of it. That's A1, and this outer area is A2, okay? And the whole thing is A3, but we'll get to that just now. Okay, I'm going to say plus rho V2 n2 is also cos of 180 degrees because the angle between the normal vector and the velocity vector is 180 degrees multiplied by area 2 plus density multiplied by velocity 3 multiplied by cos of 0 degrees now, and that's because the velocity vector is in line with the normal vector, multiplied by area 3 is equal to 0. So now that we've got all our terms down, let's try and rearrange and see if we can get some cancelling going on. The first thing I notice is that if we divide throughout this equation, we can divide throughout by rho. So all the densities fall away. Okay, and that's 0 divided by rho, which is still 0. Next thing I notice is that this is cos 180 and this is cos 180. So I can actually move it to the other side of the equation and it will remain positive because cos 180 is minus 1, move it to the other side, you get plus 1. So this becomes v1 a1 plus v2 a2 equals v3 a3. And we've got quite a nice simple looking equation from that messy one above. Let's continue. We need to now know, for steady incompressible flow, compute V3. So V3 is going to become the subject of our formula. So let's rearrange based on V3. So V3 is equal to V1A1 plus V2A2 divided by A3. Okay, before we start substituting in any more values, let's see if we can simplify a little bit further. So V3 is equal to A1 can be represented by pi over 4 multiplied by diameter squared. So V1 pi over 4 multiplied by, let's say, diameter 1 squared plus V2, area 2 is pi over 4 multiplied by diameter 2 squared. But the thing you must remember here is that area is determined, the area 2 is the outer diameter squared minus the inner diameter squared. So apologies, this should be multiplied by d2 squared minus d1 squared, close brackets. Okay, and that entire thing is going to be divided by pi over 4 d3. And remember, the outer area is this entire ring. So I'm going to call that diameter 3 squared. That's equal to V3. It's getting a bit messy now, but what you'll find is if I pull out pi over 4 from the top and I cancel that with pi over 4 at the bottom, we end up with something that looks a bit nicer. We get V1 d1 squared plus V2 d2 squared minus d1 squared, close brackets, divide the whole thing by d3 squared. It's equal to V3. We can now start with our substitutions. V1 is 40 meter per second. Diameter 1 is 0.076 squared. Plus velocity 2 is 3 meters per second. And it's the annular region around the small pipe. So we already know that it's this big diameter minus this big diameter. So we're going to put in diameter 2, which is 0.25 squared minus 0.076 squared, close brackets. Divide the entire thing by diameter 3, which is just the big diameter. So 0.25 squared. That should give me V3. And if I finish it off, V3 should equal to 6.42 meter per second. And that's it. I hope you found this helpful.